This is the ELTE260 Module L Siemens HMI lecture video. So what we have is a PowerPoint that you can click on to get this video. You're going to stop a few times when prompted. There's a worksheet to fill out. Turn to complete lecture worksheet. Here are outcomes. What is the main purpose of an HMI? Explain how local tags are different than controller tags with respect to HMI programming. Describe the difference between the different types of animations that are utilized on an HMI screen. And what are 4 different types of HMI applications? Before we do this, let's take a review of Module K. We did Siemens Counters. Counters and timers came in as a block instruction, similar to they did on the SLC 500. A little bit like FBD. Counter up and counter downs worked pretty much the same as they did on the SLC 500. Q is the done bit. When the accumulated value, CV, meets the preset value, that's when it becomes true. And CU is the enable bit. So that's why would you use this? Well, basically any time that this becomes true, usually when you're pushing the button to advance it, the CU came true, and whether you use that or not, it's kind of redundant on the push button to this, but it is indicating that the counter is true. Okay, and then I had a reset. That when the reset went true, the counter reset. Okay. Timers, the TON and the TO off, timer on and timer off, look just like the SLC 500s, work just like them, SLC 500s. The Q was the equivalent to the done bit. The IN was equivalent to the enable bit. And you set the timer, and the ET was the accumulated time. So pretty much straightforward as you fill out your worksheet. Pulse timer was a little bit different. It sends a pulse. And what all you had to do was make the pulse timer come true for one scan, and then all of a sudden it timed. It's kind of like the off delay, where once you let go of the button, it timed, but this time's on, not off. So even if you push the IN in the middle of the timing, it doesn't reset. It just keeps going until it gets done. Similar to maybe like a timer timing bit, but a lot of times it would be used for maybe sending some type of an interlock or crosstalk interlock to another controller, because if you wanted a brief quarter second, you could just close a contact for one scan, and then it'd pulse on for a quarter second or something. We talked about the asynchronous timer scan. Using the timer bits, the .q and the .in got a lot of people in trouble. I recommended putting a tag, an M bit tag associated with the Q and with the IN, stuff like that, and then using that in your program. Otherwise, you get a continuous scan of the timers, an immediate scan, and it resets the timers. Same thing when using the counters. I recommended using an M bit tied onto the Q so that you didn't get a reset of that. So we had pulse timer crosstalk. Some of the things that we were having problems with, trying to get a timer to start another timer, directly in series here. I don't recommend that. Some of these timers are going to reset and do some silly things, because when you're trying to look into them, that it's going to cause them an instantaneous read, and then they'll reset in the middle of it. So you had the counter here, and you had the timer 2.q. This looks into that timer 2.q, which is here, and so this is going to reset. And so what I really recommended was putting some type of a bit off of the Q here, let's say an M0, and then have M0 advance the counter. And definitely don't put these in series like this. And then another no-no here was on your crosstalk, to have the output coming right off of the timer. You kind of lose track of of your outputs. I like to have a bit here and then have another rung with a bit turning on the output. Okay, so this is going to have a lot of problems here because you were accessing the timer and counter data bits directly throughout this program here, causing a lot of instantaneous reset of the timers and counters, and people were having a lot of problems. So the crosstalk interlock lab was interesting. We had some good results there, especially from when you planned it. I want to remind you it was a group project. People who worked together in a group did well, and and the problem solving is pretty powerful. So if you understand something or you don't understand something, you bring that to the group. And if somebody else kind of understands something or has pieces to the solution, then all of a sudden when a few people get talking about the way something's supposed to work, all of a sudden everybody kind of realizes that that's the way that it's supposed to work. So the purpose of that was the group project. And now we have the capstone coming up in a couple weeks, and that's a big group project where you're expected to work together with a team. And so the mistakes we had was they used the counter.q to send a crosstalk and also to reset the counter. So it never got the crosstalk going because the .q gave me an immediate read of this and reset it. That didn't work. I recommend using a bit, M, and then tying that to the counter reset. Using some type of a pulse timer took care of resetting of the timers, because a lot of times you wanted to signal the other controller, but you didn't want to keep something held on, so all you would have had to do was make the pulse timer true briefly. Then, when the counter gets done, all it's got to do is for one scan make that pulse timer true, and then that pulse timer would pulse over a quarter second to hold that relay down, if you can imagine that, and then you could reset the counter and the pulse timer would die after the quarter second. But it wouldn't reset immediately, because as soon as the pulse timer is made for one scan, it's going to go ahead and hold that crosstalk relay down for a quarter second. And then using the relay contacts to use as a crosstalk and trigger for the reset is a pretty good idea. I'm going to show you that in a minute, because what happened was after you had your timers, you had your blink timer and your reset timer getting done, and then you wanted to have the counter count 3 times and then close that relay. Well, you didn't want that relay on, so you had to, sometimes you had to have another timer in there to let go of that relay. So there's different ways to do it, whether you used a pulse timer or that relay contacts or something. And so the timer does work. I showed you prior, but I don't recommend it. I'm putting them in series. It's better to use bits and kind of break them out and be sure use use a M bit associated with that done or that Q bit. Take a look at this Interlock lab solution video. I'll show you some ideas there. So the homework we're going to take a look at here, hopefully you're doing well in the quiz, and I'm going to take a look at 4 different solutions for that last part of that last quiz that we had. So that last quiz was a jog run, and so here's the first way that you could have did it. You could have made a motor function block, and you could have just scheduled it once. The quiz did ask for you to come up with 2 different functions, one for run, one for jog, but if you just wanted to put them all into one like this, this would work. So here's my ladder logic inside of it, and so basically I have a run jog right here. So when this is unconditionally scheduled, so my run jog is either going to be true or false. So this is either going to be open and closed, or this is going to be open and closed. So true or false or true. Only one of these rungs right here is going to execute based on the run jog. So then start gets used once, stop gets used once, auxes get used once, all these inputs get used once and plugged into here. And so if you're on run jog, let's say this is true, and the stop is where it normally closes, so that's true. Well, when I hit start, I'm going to get the motor on and the aux is going to hold if the photo is made. Okay, and then going the other way, if you click it over, it would go offline because it wouldn't be running right away because the prox wasn't made, so the aux would drop out. And then this rung would not be true in any way because that's open and now this is closed. So when I hit start, if the prox was made, it would turn the motor on. This aux would close right here, but it doesn't matter because this is false when this is true. So function block's one way to do that. Another way was to kind of take that logic and put it into two. So I took the first rung of logic and I put that into the jog, and then I took the second bit of that logic and I put it into run. And so the selector switch conditionally schedules either the run or the jog. They both can't be scheduled at the same time. Okay? And so what I would do is I would take a jog bit and a run bit, and I would return those out of the subroutines to the main here and put them in parallel, so that if for some reason the jog bit was on because we had the start button pushed, then it would jog it. And if for some reason the run bit was true and if it was held because it's got auxiliary here to have memory, well that would true. So and that way I only use an output once. Okay, so this is kind of an option here. Got to remember though that if this right here is true, okay, and that we switch selector switch and jump out of it, it's going to try and keep this true. Okay, so that when we toggle back into the run, it's going to try and make this true if that's the last state it's in. But that's why it was important to have that auxiliary contact here, because that likely was going to drop this circuit out as soon as we rescheduled the run, because if we were in the jog and it was off jogging, when it comes back into here, the aux is immediately open, and even though it might have thought this was retentive, when we jumped out, it immediately would deactivate. Here's another way where we schedule the output twice. So this works. Not a big fan of it. Basically, put these same logic into the routines, and selectors does one or the other, and therefore the motor is going to be running or not running. And so the problem is that we've used the output more than once, and so if for some reason I'm jogging, let's say I'm jogging here, and I got the start button pressed, and this is jogging, and I hit the selector switch, okay, and I go into the run, make that true, and then I come back into here, you got to be aware that this motor may think that it's still on inside of that subroutine, if that's the way things were when it was being scanned. Okay, especially on this one that has the holding here. The auxiliary contacts probably take care of that problem, but it could be a problem. And then here was a fourth solution. If you just threw this ladder logic into a network, it'd be nice if it was scheduled. And so that's how I showed you that you scheduled it twice, or you'd schedule it once into a function block. But rather than just throwing this ladder logic into just the main, I was looking for a little bit of scheduling on that. Topics are networking and HMI. So a human machine interface is shown on this right here, YouTube. So go ahead and watch that real quick, and you'll see the applications in industrial automation are evolving, but currently consist of, when we're talking about a touch screen to control a PLC. This video right here gave a lot of other things, and some of that seems a little high tech, you know, talking to a computer and getting a machine to operate, and and retinal scans and all that, but all that is versions of human-machine interface, and we'll get there someday as far as automation and PLCs. It can be connected to a communication with a PLC to replace push buttons, switches, pilot lights, thumb wheels, and other operator control. So, for example, thumb wheels used to be a way that you would kind of click numbers to enter them into a machine to get a recipe. Nowadays, you just, on this screen right here, if you want to make 12 items, you just click 12 and click enter, and then it makes 12 parts. Or if you want to start a process, you can just start it here. Okay, so the HMI is a way to push data and push, whether it's Boolean or registers or something like that, into the PLC, and it's also a way to read the status of those items while the PLC is running. They allow you to view the operation in real time, so it's pretty common to come up with an HMI screen that's got a lot of detail here that's showing you your process, your mixing tanks and your heaters and the flow of material, so that you can kind of see what's going on, and you can go deep into the menus to get an idea of what each one of the tanks is doing, each one of the motors and everything like that. So once again, it replaces a lot of those hardwired push buttons and stuff with realistic looking icons. It shows alarms and times and how well the process is running. You can change timer and counter presets and recipes to get things running longer. If you need to mix this longer, you need to heat this longer, you can make those changes on the HMI without having to get in and reprogram the PLC. So the applications are recipes. That's changing formulas and like timer and count values, or how long something is occurring, or how many times, or how many chocolate chips you add to the cookie dough, things like that. Just like that. Event logging, so that's faults and alerts. The HMI will keep track of all those, so you can look back and find out why the process stopped, what was happening. A lot of times it's tied to a big bingo board that shows the status of all the inputs and outputs and the status of the process. Video feed, you can use the HMI to kind of look into the camera systems and see what's going on in the process. And then also your event triggering, it kind of replaces your control panel with your start and stop and all that kind of stuff. So your types are a push button replacer, just like a control panel. It's a data handler, so it can take your data and you can put your reports up and your recipes and your logging, and it just tell you how everything's going, or if there was an alarm and the system shut down, when it happened, why it happened, things like that. And it also can be involved with SCADA, which is your supervisory control, and this is very complicated, but it can be involved in all the data if there are multiple processes in how PLCs get tied together, and you can just look in and see how your facility is running and all that kind of stuff. We have a pretty complicated system downstairs, which is the Flex. So either take a tour of the Flex, or you can watch the Flex tour video link here that talks about some safety, and it kind of shows you some of the HMI functionality and stuff. So HMI programming. Buttons are added to an HMI screen. So when you build a control panel, you have to actually hardwire in a button. Well, when you build an HMI, it's fictional. You just kind of drag a button onto the screen. It's a lot quicker than cutting a hole and installing a button. Just drag an icon and making a button on the screen. They can be square, round, user created. They can be animated. So they change color when activated. And once again, a lot simpler than if you have to switch out a red button or a green lens or something like that. On a control panel you could, but on HMI you can do that as well by just fictionally changing it. And so a button gets assigned an internal bit address because they don't really exist. So they get addressed like they're a push button, or you put a light onto a panel, they get addressed like they're a light. But you use M bits because they don't really exist. Whereas your push buttons do get I addresses, and your lights and stuff like that do get Q addresses because those are tied to things that exist. Okay, so HMI components get internal bit addresses M. So here's a couple of examples of setting up an HMI program. So go ahead and watch that. Just remember of HMI fiction. The HMI buttons and indicators are not real. They're programmed onto the screen. Therefore, HMI buttons should not be used for an e-stop, because if the screen gets broken or somebody steals the HMI or something like that, that's not the same as an actual e-stop getting damaged or being pushed or being removed from the system. An actual e-stop is a hardwired device that's going to bring the system down and kill it. Because HMI is fictional, it's not going to work like that. So HMI should not be used for e-stop. HMI buttons can be used for a stop, but just not an e-stop. HMI buttons and elements should not be used for PLC monitoring purposes. Well, what does that actually mean? Well, they kind of are used, like I said, with bingo boards and stuff like that. So it is nice to see what is going on with the PLC, but you have to be aware that there is some lag time between the HMI buttons and elements and what you're seeing on the screen. Okay, it's not instantaneous. And so if you're going to use the status of those buttons for more control, that could maybe get you in trouble. Okay, so they are used for indicating what's going on, but when we get into more advanced topics of monitoring devices and dual check safety and stuff like that, you'll see that HMI is good for indicating, not fully suitable for safety control. Okay. Our network connections. So HMIs need to be connected to the PLC using a static network through a switch. So this shows an example here of a switch, and there's some drives and PLCs and everything that all run into this, and then this runs to another switch and runs something to the LAN, and this can be connected to other PLCs and other devices and other computers, and kind of similar to what we have going on with the World Wide Web, where you're fully connected. And so if you set this up, you can connect to a lot of devices in your facility. On the worksheet, there's a Star Network video link here that you want to take a look at and fill that out. And so that's about it for HMIs. The lab should be pretty straightforward. So you have a quiz and then your lab.